Good morning, everybody, and thank you for this opportunity. And this is now it's perhaps the fourth day of our capacity building program. And yesterday, I started with some introduction to some technical components of hydropower projects. And as we had the case study presentation by Mr. Constantino on the Majau mini hydro project, I stopped. I did not cover all the presentation materials that I had planned for. So I will continue from the presentation of yesterday. So actually these presentations, especially I think the first session, I will cover what was not able to be covered yesterday. Okay, coming back to small and large hydropower projects layouts, I started with the layouts components of the mini hydro projects, which are slightly on a smaller scale. But I just wanted to introduce you to a little bit larger size, small size hydropower projects also. And basically, the mini hydro projects, micro hydro projects are run-of-the-river projects. And basically, they either use headrest canal or headrest pipe. And these are the same layout components are also applicable to small hydro projects. So on the left, I think somebody's anyway.
Please, Divas, please, you have to actively mute everyone that comes in. Otherwise, it will be very difficult to understand.
Yes.
Mr. Vilankoulos, could you please mute your audio?
Yes, Divas. Let me just ask my colleagues, all the participants, please keep your computer on the mute mode. Por favor, desliguem os microfones do computador, tirem o som do computador, por favor. Está a haver interferências. Colega Vilankoulos, por favor, põe o...
Mr. Cesar? Mr. Cesar, could you please mute your microphone? Thank you. Mr. Kemal, good morning. Could you please mute?
Yes.
Okay. Thank you very much, everyone.
Okay, sorry, let me. Okay, so I mean, sorry for the the breakup. Okay, basically, I'm talking of two types of run-of-river hydro projects. One uses the headrest pipe, and the other uses the headrest canal. And also, the third type is that you can use a tunnel system, a headrest tunnel, and this tunnel basically is on pressure, under pressure. So the water that flows under the headrest tunnel covers the whole diameter of the tunnel, and it is under pressure. And then at a certain point, it's basically underground, as tunnels are supposed to be. And then finally, we come up to the penstock, which leads to the powerhouse stations. Basically, tunnel development started in the middle 1900s. So initially, most of the tunnels were more horizontal tunnels, but later on, after some development, we are also using tunnels which are pressure tunnels, as I mentioned, since 1975 or so, in the 70s. Then these are basically on also on a because the equipment for tunneling work has improved. The technology has improved, so the tunnels are now mostly under pressure, and you also have nowadays powerhouse which are also underground. I mean, for various reasons, for some of which are for using the increasing the head also. So, so these are the basic layouts of run-of-river projects. And some projects transfer water from one basin to another. And so one river to another river. And this is basically very common in mountainous area, so that you can utilize the head difference between one river and the other. So this is the one other type layout conditions. Then we have projects which has a dam that stores water. And basically these dams that store water are also have different types of layouts. Some of these dams have their powerhouse just at the toe of the dam. Okay, dam of the powerhouse just at the toe of the dam. But some other projects have another headrest tunnel where the powerhouse is located certain distance away from the dams, from the reservoirs. So this gives you additional head that can be utilized for power generation. And the third type of hydropower, which I had earlier mentioned, are the pumped storage projects, which uses the additional energy, cheap energy at certain periods of the certain time to pump back water from a lower reservoir to a higher reservoir. And when you have this differences on pricing and also differences on supply and demand of power available, then you can utilize power that are not used at off-peak hours. Sorry, let me just, I'm a little bit mute. Can you actually, I request the participants entering, because sometimes I'm I'm having problem muting while I'm talking. So please mute yourself if you when I admit you to the Zoom session. Okay, thank you. So these are the pumped storage layouts that are mentioned, and I think we have already talked about this quite often. Okay, now for a mini hydro projects, what are the preliminary data that needs to be collected? Okay, so when you are planning for a mini hydro projects, it is important that we collect some data which helps us to decide on the layout of the hydro project, as well as even to decide on the capacity, and also to decide whether the available energy and power that can be generated from a particular river is enough to meet the demand that it needs to serve. And when I talk, because mini hydro projects, especially if it is an isolated mini hydro project, it is important that, because they do not have other can you just since they do not have alternative power supply, so this particular mini hydro project, unless should be able to meet the normal demand of that load center. So the important data that needs to be collected basically corresponds to some of the key design parameters. Like I mentioned, first of all, the install capacity, is it enough to meet the demand on lighting? It's not lightning, sorry, there's a spelling mistake. end uses, other end uses, site-specific features, as if there's a tourist place or a small hotel or small-scale enterprises, the demand that should be, the supply should be enough, the capacity should be enough to meet this demand. So we need to collect some consumer demand estimates and the population, the types of end users they use, and other socioeconomic items. And the other important thing, of course, is, as you know, hydropower generation has two parameters which are very important. One is the elevation difference between the location, the potential location of the weir and the powerhouse. So this head available, and also the flow, the stream flow, the water available in the river we should be able to have a quick estimate. And normally you have a gazing station in such locations, but not all hydropower sites will have a gazing station. So you have to be able to find ways to estimate what would be the flow available. And when I talk about the flow available, you have to be able to find the variation in different months of the year. In 12 months, how would the flow vary? Because when you have the rainy season, the flows obviously increase. But when there is no rain, the flows decrease on the rivers. And the minimum river flow is an important parameter that needs to be sort of gauged in the beginning. And you can, for that one, of course, you can do some very simple flow estimation techniques. I will talk about it a little later. Or you can also ask people what will be the level of flow available in different months. So you can take the opinion of the communities living on the rivers to give you an idea of what is available. You may need to also talk about what are the market possibility of grid connection. Suppose, what is the grid connection, national grid? What are the chances that this particular area will be connected to the grid? So there has to be some coordination with the national utility. And of course, I talk about possible income and expenditure. The reason we talk about this, what is the willingness to pay or willingness to accept the tariff? And so it's good to also gauge these the economic condition of the consumers. And of course, management, environmental, socioeconomic factors, some initial data should be collected, because this will be important for the ownership as well as the acceptability and the need assessment of such a mini hydro project. And also, finally, you have to have the interest of the people to implement. You have to look at the sources. What are the sources of funds that are available to implement? So you have, nowadays, you have private sector, communities managing their own hydropower projects. So are some other sources of funds available for funding? I think it is good it will be good to get that preliminary information collected also. Now, for a site selection and scheme layout of a mini hydro project, as I mentioned, these are some of the initial data that should be collected. One, as I mentioned, is the head available and the flow available. I already talked about it. What is the flow availability? At least it should be available 11 months. Maybe 1 month you can have some main deficit in the flows, especially if it is a standalone isolated system. Okay, so at least 11 months of the time, the power generation should be equal to the installed capacity. That means that 1 month you may not be able to generate in full capacity. So, from what I understand, the Majao mini hydro project, for example, generates at full capacity throughout the year. So the water available at the weir section of the Majao mini hydro project is more than the design capacity, design discharge, I think, which is around 4.5 cubic meter per second. So the topography, sometimes you can use simple survey equipment, what we call as level machine, just to get the level of the of different points. Also, nowadays, you have global positioning systems, what is known as GPS. You have handheld GPS that uh, can be used. You also get a compass to get the survey, some mark the layout, the possible layout in the topography. You also should look at the slope stability of the slopes, because it can affect the design of the components. Because when you design or plan the alignment of the pipes or the canals, you have to make sure it doesn't fall under or below an unstable slope. So it is important to get an idea of the conditions of the slopes, the topography, because hydropower to a certain extent is more feasible in hilly areas. But hilly areas means that you have hills and slopes that can, some rockfall, some landslides, and other debris can fall into the different components of the hydropower projects. So we have to be careful. The layout options, you may have multiple options. So you have to find with experience, and you have to find the right optimal layout of, let me just, there is some people who entered who are unmuted, so I need to just check. Okay. Uh, uh, and the other thing, as I mentioned, is the power generated enough to meet the demand of the area that I already talked about. Also, hydropower project has to also sort of align with other multi-purpose uses of the project or of the area. For example, if you divert water from a river for hydropower purpose, at least for some section of the river, you may not have enough water to meet for water supply, irrigation, and other purposes. So if you can plan the project without disturbing the water supply and other irrigation and other water uses in the river, that would be preferred. If you need to, normally hydropower is non-consumptive, so it will not really use water like for water supply or irrigation, but the area from the weir and the tail race, if you divert water from one river and drop that water, release the water in a different location of the river, then we have to be careful that it doesn't disturb the other uses of water. So these are basic, very simple principles that you use to decide on the system, site selection, and scheme layout. We will go into the details of these during the course of this capacity building program, especially when you do the feasibility study capacity building. So we'll do some exercises. I'll try to get some real situation, real data, and work on it. So, but at the moment, I just wanted to give you an idea of what is expected. Basically, the outline will be, I will talk about different design parameters and some conceptual things about the hydrological cycle. Then I'll also talk about the power and energy computation. A case study was already done, so I will not talk much about that. So as you know, the hydrological, this is a very general schematic of the hydrological cycle, okay? So we are, as a hydropower designer or a planner, we are interested on the surface flow, outflow, the river discharge, okay? But what occurs in the rivers passes through different hydrological processes. Obviously, precipitation, rainfall, especially in Mozambique, you don't get any snow. So in countries which get snow, they get snow and or rain. Whereas in countries with don't get snow, it's mainly rainfall. So whatever falls as precipitation, part of it evaporates back through plants from uh, open lakes and open water surfaces. Then some of it will directly come as what is known as the surface runoff, whatever just overflows from the surface. Some of it infiltrates, okay, percolates on the ground. So depending on the soil type, land use, the infiltration, percolation occurs. And it is very important to have this infiltration and percolation because it recharges the groundwater aquifers. And this groundwater aquifers are the sources of the dry season flow. So when there is no rainfall, you still see water flow in the rivers. So that flow water that you see in the river when there is no rain above you is through what is known as the base flow or groundwater flow. So it is very important that the catchment area is, I mean, if it is all covered with concrete, there is very little groundwater recharge. So the water available in the dry season in such places will be low. But if you have a catchment which are forested and which has open surfaces, then you can have groundwater recharge, which will come back as the base flow in the dry season. So it is important to understand the hydrological cycle, because by understanding the hydrological cycle and the processes, the different processes of the hydrology, you can estimate the flow available in the river in different time of the year. So this is very important. And of course, I will not go into the details of all the processes, but I think understanding this is very important. Okay, the next one is for a hydrological study, we need hydrological and meteorological data. Okay, when you talk about meteorological data, we need basic information on what is the rainfall. It's good to get some information on the temperature, okay? What is the temperature in that area? And of course, what are the water level? What are the river flows? It is also important to get an understanding of what is the sediment, because if you have a lot of sediment in the river, then you have to design your settling basin to separate the sediment from the flow, because in the turbines, if the sediment load is high, if there is sand and a little bit larger side silt sediments, then the turbines can be destroyed. So the efficiency of power generation is reduced. So you have to have some basic information on these parameters. Other information, as I mentioned, air temperature, water temperature, all these, this is directly not related to hydropower itself, but this can affect the water available. So these other information is important. Although for a mini hydro project, we don't need to go into the details of these other information. Now, because to estimate the flow available, we need to know the exact location of our project site, okay? The latitude, longitude, because we have to look at the topographical map and we have to sort of delineate the catchment area. And the catchment, by catchment area, I mean the area. Suppose you are making a hydropower, there's a river and there's a project here. What is the area from where the water flows? So that is what is known as the catchment area. And it depends on the topography, okay? And so based on that, you need to get the basin or catchment characteristics. I talked about the area. What is the area? It is 500 square kilometer catchment area or 1000. Larger the catchment area, the higher will be the flow. So it is important, okay? But larger catchment area also means that it will have higher floods. So you have to design your structures to manage large floods. So it's good to have big catchment area, but it's also important that we are able to estimate and manage the floods. I talk about the shape of the catchment area, the length of the catchment area, the slope, the drainage network, what is the land use, land cover. These factors will impact or affect the flow availability. As I mentioned, in the hydrological cycle, whatever rainfall the catchment receives, these will be in the catchment, it will be transferred to the rivers as river flows. On the right here, on the map of Mozambique, I have shown what is the elevation differences, okay? So you have, of course, on the coastal area, you have low elevations, less than 100 meter, even less than 30, 20 meter. But you have, the mountainous areas are on these things, hilly areas. So I would assume the darker it is, our mini hydro projects or hydropower projects will be located in these darker, higher elevations. For example, the Kohora Bassa reservoir is somewhere here in the I think it's Zambezi River Basin, right? Zambezi, if I got it correctly. So these elevation, no, these data are from the digital elevation models. Okay? Digital elevation model data nowadays are also, you can get it through satellite data, and the resolution of this data is important. So I will not go into details, but as we do the exercise later, I will show you how to delineate the catchments, not today, but later in December or January in our courses. So this is the digital elevation. And I don't know how many of you are familiar or have some knowledge with GIS, Geographical Information System software, like QGIS, ArcGIS. And basically, as a hydrologist or a hydropower engineer, it would be good that you have some basic, and as a planner nowadays, some basic knowledge of the GIS software would also be useful for you to do hydrological analysis and other type of spatial analysis. Okay, so this is on the right is basically, this is the Zambezi, right? If I pronounce it correctly, correct me. This is the Zambezi River Basin that flows, as I mentioned, Kohora Bassa Dam is somewhere here. This is the elevation difference. It covers, of course, the lower catchment is Mozambique. It's very a large river basin, and it flows, part of it flows through Malawi, Zambia, Zimbabwe, Congo, and Angola. So, okay, and I understand there are a number of reservoir projects upstream. I just show this to you because if you are doing a design of any project here on the mainstream of Zambezi River, okay, the Kohora Dam is here. So this receives water not only from the area within Mozambique, but it receives water from all this whole catchment upstream of this location. The Kohora Bassa Dam is, for example, here. If you are doing a hydrological study of the Kohora Bassa, what is the water available? You will have to consider all the catchment water uses, the rainfall that occurs in the whole catchment, and how it is available in this location. So other basic data, as I mentioned, is that other human activities, we have to know what are the existing plants, hydropower plants, because you don't want to disturb their flows. What are the reservoir upstreams? Because these reservoirs will control, regulate water, okay? So it's important. What are the water extractions for irrigation? Suppose you make a hydropower project in a small river here now, you design it for design discharge of 3 cubic meter per second. But if in the future, there will be an irrigation project that will divert water upstream of your hydropower project, you will have problems with the water available. Normally, data available should be 30 years desirable. But I mean, most, especially mini hydropower projects, which are located in remote areas, do not have that many years of data. And they say 15, 20 years is acceptable. Even if you do not have those data, then you can use models, which are known as rainfall runoff models, or also you can use regional analysis. By regional analysis, what I mean is you can transfer data from a hydrologically similar catchment, from a data from another river nearby, and using the catchment area ratio and other climate variables, you can estimate the flow available. And then once you get this data, you have to do some reliability and consistency checks of the data. And this is true for any type of data. No, you collect data, you have to be able to check the quality of this data. You should also investigate the historical floods. What are the flood marks in the river? What are the water level surveys should be done, so that you know when you design your powerhouse or other structures, these structures are able to manage these floods. And for the Majau mini hydro project, I think it's an interesting case study we'll discuss with Mr. You must have discussed yesterday, because in 2015, I understand the heavy rainfall in 2015 caused flooding of the river, which destroyed, I think the powerhouse was flooded, and the turbines, generators were damaged, if I'm correct. So you have to make sure you know the flood marks. And when you talk about flood marks, it is not the flood level that occurs every year. It meant, like, some you have to be prepared to manage floods which occur once in 50 years, once in 25 years. For very large projects, you have to design your hydropower projects for 1 in 10,000 year flood, which means the probability of that flood occurring is once in 10,000 years. Because if that flood occurs, if that hydropower or reservoir project is damaged, its Kahora Basa Dam must be designed for considering a flood risk, a probability of 1 in 10,000 year, or even probable maximum flood, theoretically possible flood. Because it is important that, because such a huge structure, a reservoir, if there is some damage, it can affect lives and livelihood of many people in the downstream area. For mini hydro projects, you don't need to design for such high floods, because even if it is damaged, you have economic losses, but losses to death or livelihood or lives of people is very less. Okay. Now, I will, since there were some disturbances, it is around 8:56. Let me just continue for 5 or 10 minutes more, so that you can have a shorter break if you don't mind. But regarding the meteorological climate data, first of all, rainfall is the most important data. Okay, over here, I show you the rainfall variation using the data, satellite-based data of NASA. I can, maybe in the exercise later, I will show you, if somebody is interested, I can show you exactly how you can download this data. I just downloaded this data on the NASA website, okay? And this is, they have like every 6 hours data. So in fact, if you go to their site, you can get the rainfall for today, for anywhere in the world, okay, including Mozambique. So this is the data. But of course, this rainfall data is satellite-based gridded data that I downloaded for this purpose, and I will little bit show you later. The more darker side receives more rainfall. And apart from the satellite data, these satellite data are good, but it has to be checked, validated using ground data. So I understand Mozambique, as the meteorological department, collects data at different locations of Mozambique. So that is, because that is ground data. So these satellite data should be checked with this ground data. And normally, I mean, to be honest, for a mini hydro project, because you do not normally go into the detail of using all this satellite data and doing the analysis, because sometimes available ground data and just doing your basic hydrological study is enough. But now, since these type of data are also available, I just wanted to bring it to your notice. The other meteorological data, yesterday, Paul presented about, and you have, of course, a map of what is the solar energy potential in Mozambique. But you see nowadays, and I'm sure there are weather stations in Mozambique that is installed by the Department of Meteorology, and I would like to hear from you if such is available. They will collect data not just on rainfall. Of course, they collect temperature and rainfall is common. They also collect data on evaporation and evapotranspiration, because this is important to, I mean, this is not so much for a reservoir project, evaporation is important, but for mini hydro, not so much. But for other water projects like irrigation, if you want to get the irrigation water requirement, the crop water requirement, this data is very important. Relative humidity is important. Solar radiation, nowadays you can have these meteorological stations, automatic stations, also measure data on solar radiation, on how many hours of sunshine you get in a day, what time is the sunrise, what time is the sunset. You also get data on wind speed. So these are, I just wanted to, since we are covering a little bit the session on hydrology, I also wanted to know, and most of you might be aware, but I just wanted to highlight these climate data are also available. Okay, and regarding the rainfall data, there is, as I mentioned, this one was the satellite-based data from NASA. Okay, and this one, and you have other sources. You know, this is NASA is one source called. They use what is known as the TRIM satellite, TRMM and GPM, and they have their own. But there are other satellites worldwide, Japanese satellites and the European satellites, which also collects this data. But the data using rain gauges are, you see, like different locations in Mozambique have rainfall data that is measured by your Department of Meteorology. And you also can have radar observations are also used, and satellite estimates, as I mentioned, is from agencies like the NASA, US government's NASA. So but you measure data from one point. Now you have to convert that data on the whole area, okay? So what is the rainfall available in the whole catchment? So you have different methods. You take the arithmetic mean, what is known as Thesian polygon, isohydral method, and other geospatial methods are also there. So I mean, we can cover this if somebody is interested. I can tell you separately, I can do that, but today I will not go into this detail. But one thing you have to be a little bit understand is, you see now the rainfall variations from here on the lower southern coastal side. Here, for example, you have a annual rainfall of 860 millimeter. Here you have 635. In other locations, you have 1100 and 1000 thing. So basically, I think the average rainfall in Mozambique is around 900 to 1000 millimeter. Now you also have to be careful that your rainy season in Mozambique starts sometimes in November and ends in April, May. So from April, May to October, November, the rainfall is low. Similarly, it is expected that the critical flow. Okay, let me continue. Carlos, you hear me?
Yeah, we can hear you.
Okay, good. So, okay, now basically, I want to now go over the key hydrological computations that will be required for a design of mini hydros and even small and larger hydros. First, as I mentioned, you have to collect data at the catchment data, the whole area. Then you have to now get the runoff data or discharge data. So on the right here, this is data of a catchment in the border of Malawi and Mozambique. And you can see that the rainfall varies, as I showed. It rains from, let's say, November, December till April. So the flow is higher in February, March, but reduces, and the minimum flow is around in September. On the left y-axis, y1 axis is the discharge in cubic meter per second. So it varies from more than 30 cubic meter per second to around 4 or 5 cubic meter or 3 cubic meter per second in the dry season. So we have to first do the computation of the runoff. This is what I mean by the runoff. Then we also have to know, compute what is known as the flow duration curve, which I will go in detail in next few slides. And then we have to do what is the minimum flow. Then we have to also calculate what is the maximum design flow. What should be the design flood in the weir, in the dam. So we have to decide. Then also we have to see the stage discharge relation. I will also show you this. By stage discharge relation, what is the water level when the flow is 30 cubic meter per second? What is the water level in the river when the flow is 3 cubic meter per second? So this is something that we have to compute. Then the sediment analysis also is important, as I mentioned. And for basin, without good data, you can do this data analysis or computation using data from hydrologically similar catchments. Okay, some nearby station, you transfer, you get an analogy of, depending on the catchment area, we can derive new set of data. And for hydropower projects, when you decide to do the hydropower projects, some temporary weather stations and water level stations are established. Okay, so this is the hydrological computation introduction. Then the first hydrograph or the runoff is the variation of the discharge in the river over the months from January to December. Okay, so by hydrograph, I mean the plot of the discharge in a stream plotted against time chronologically. You can plot this on a daily basis or a monthly basis and yearly basis. Now, there are basically three types of runoff situation, okay? Some rivers are perennial. You have 12 months, you have flow in the river. So these are rivers with sizable catchments and sizable rainfall. But there are some rivers which has zero stream flow in the dry months. I'm sorry, the data I use here are from other part, not from Mozambique. So the wet season, especially this is from Asia. So the wet season is in different months, so it will be different. But what I mean to say is intermittent means some months of the year you have no data. So if you want to do a hydropower project here, without storage, storing some water which can transfer to the dry season, a hydropower project will not be feasible, because 1, 2, 3, 4 months, you will not be able to generate any energy, power. And the third type of catchments or runoff are very small, what is known as euphemal streams. These are, whenever there is rain, you have discharge. Then after, when there is no rain, there is no discharge. Okay, these are, in fact, these are for in very small catchments, but these are rivers also. But rivers, where there is no flow most of the time, but whenever there is rain, there is this flow. And by runoff, as I mentioned, runoff is the whatever precipitation that falls in the catchment, what comes in the river is the runoff. And basically, uh, there are two types of runoff. One is direct runoff and the base flow. And as I mentioned, base flow is based on groundwater storage, which is coming back to the river. There is a groundwater surface water interaction. So that's why even when there is no rain here, there is no rain or very little rain, there is flow in the river. This is because of the base flow. Okay. Now, talking of runoff analysis, we have to basically, like for example, this is, I'm not sure if it is correct, but this is because the location of the Majau mini hydro project. I just did a catchment diagram for Majau. I mean, of course, most of the catchment lies in Malawi, but there are some parts that lies in Mozambique. Okay, so the powerhouse dam, the intake is somewhere in the Mozambique side, but it looks like it is very near the border. I mean, this is subject to the exact location. This location from Google map. So there could be some, maybe if like I put it in the main here stream here, but if it is in this stream, in this tributary, the catchment would be smaller. And these small green dots are some of the rainfall stations available in Malawi. Since our catchment is very close to these stations, we could use the data from these Malawi river stations and derive the discharge data for Majau. So, and for that one, since there is no data discharge gauging station in this dam site area, what we do is if you use this data to transfer to here, we take the ratio of the catchment of this station, the green station here, and the catchment of the whole catchment, the ratio of this area, and using that ratio, and also we take the relative precipitation that occurs in this within the catchment of this station and this catchment. So we take the ratio of the rainfall as well as the catchment area, then we can derive the discharge at the hydropower station. So this is what is known as deriving discharge data where data is not available, using data from a nearby location, from a hydrologically similar, homogeneous meteorologically conditions. Okay, so rainfall pattern is more or less same. Then you can use this method. And in mini hydro projects and most projects, because you cannot get data in that particular location for a long time, you basically use this method. Okay, and now this flow duration curve is a very important part for hydropower. Okay, because we will know what is the percentage of time the flow is available. Okay, the flow duration curve, this is the flow duration curve of this green point here from this Malawi. I just got this data from the internet, and I drew this curve. Okay, this curve is basically drawn by taking all the data, arranging it in a descending order, then finding the probability of exceedance. Like out of 300, let's say out of 365 days, the minimum discharge will be exceeded 365 days. Okay, but the maximum discharge will be exceeded 0 days because you cannot get more than that. So based on that probability, like let's say 80 percentile, 60 percentile, 40 percentile, 20 percentile, this curve is what is known as the exceedance probability. And the value we get, like 95% of the time, you get a flow of 1.9 cubic meter per second or more. 80% of the time, you get 3.5 cubic meter or more. So if you want to select now, how much should be the design discharge for a hydropower project? If you select 1.9, then what happens is 95% of the time you will generate to full capacity. But if you select 3.5 as the design discharge, you will only be able to generate in full capacity for 80% of the time. 20% of the time, the energy that can be generated from that hydro plant will be less than the installed capacity. So the flow duration curve is an important hydro parameter or computation useful for hydropower project design. Okay, the next one is the design flood. Okay, design flood is basically we have to look at two attributes. Okay, one is what is the maximum discharge in terms of volume per second, cubic meter per second. The other thing is what is the water level when this flood occurs? Like especially if you are doing a flood study, if the flood is, let's say, 1000 cubic meter per second, what is the level of water in the river? Does it spill over the bank? Is it more than the bank capacity or less is important? Or if you're making a bridge, will that water level reach the deck of the bridge is important. Or if you have a powerhouse location in Majau, for example, okay, the Majau project powerhouse location, is the elevation of the flood peak lower than the powerhouse base or high? If it is higher, then what happens is water can enter into the powerhouse. And from what I understand, in 2015, something like that happened. Okay, so why we need this design flood? We need this design flood to design hydraulic structures such as weirs, dams, bridges, culvert, waterways, etc. And why do you need the elevation, the stage, the water level? Because we want to decide on the elevation of the hydraulic structures like bridges or powerhouse. What are the different methods to do this flood estimates? There are different methods. Very basic method is what is known as the unit hydrograph method. There are empirical. There is some disturbance. Okay, there are some empirical methods based on data like Dickens rational method. Regional method also is based on data of, you can make regional graphs for prepare for Mozambique catchments. Then the most commonly used is if you have the data of long-term data, then we use what is known as the flood frequency methods. We use probability distribution functions. Examples are Gumbel method, Log-Pearson type method, extreme value method, and other methods. Okay, so this is the design estimate. Now, the flood frequency analysis is done using a frequency analysis. And basically, the basic formula of flood frequency analysis is first we collect the peak discharge for every year, annual series of peak discharge. Let's say you have 30 years of discharge peak flood data. You put that, you then use, arrange this in a decreasing order of magnitude. Then you get the probability of each flood being equal or exceeding this value. And this is the formula, the order number of the event and total number. So this is the probability that the flood will be extended. And the time period, this is very important. Return period of frequency is divided by 1 upon P. And you must have heard of 1 in 100-year return period flood. That means the probability of that flood event occurring is once in 1 year. It's a probability, but mind you, that same flood can occur today, tomorrow, and day after. But the probability of occurring today, tomorrow, and day after is 1 upon 100 multiplied by 1 upon 100 multiplied by 1 upon 100. So the probability of occurring once is 1 in 100 years. Probability of occurring one after the other is 1 in 1,000 years. No, it's 10,000 years, 4 zeros and million years. So this is the probability and the return period thing. And the equation for hydrological frequency analysis is basically is here. During the exercise, we'll do a little bit of this exercise. I'll go into details in the following sessions. Okay, so this is what is the curve that we normally do. We on the x-axis we have the return period. It's in a log scale. So for example, what is the 10-year return period is around 450 cubic meter per second. What is the 10, 11, 12, sorry, 100, 200, about 200, 20, 20, 30. 30-year return period is around 450. 100-year return period is around 650. 1,000-year return period is around 900 or something. Okay, the red one is the actual projection or the probability of occurrence, and the blue one is the confidence level, but you're basically interested. So if you want to design this project for a 100-year return period flood, you have to do it for 650. This is the data for the same station I mentioned. Okay, so this is just the frequency analysis, and I also want to now to get the slope. To get the stage, the elevation of the thing of the flood. We need to what we do is we use, this is a slope area method, is a common method where like what will be the discharge. Okay, suppose the water, this is on the right in the figure here, is the water level is here. Then now you want to know what is the discharge in the river when the water level is H1. Okay, and here in this location the water level is H1, but you want to know what is the discharge. So there is one common, very simple uniform flow equation called Manning's equation, which is given as here. It is 1 upon n. A is the area, r square to r to the power 2/3, s to the power half is r means the wetted perimeter. It is the length of the cross section that is wet or there is water. So basically the wetted perimeter is, sorry, r is the radius, hydraulic radius, and hydraulic radius is divided by the area divided by the wetted perimeter, and s is the friction slope. Okay, the friction slope basically is the this is the water surface, and basically this is the energy gradient. But normally if you want to do a very simple estimate, the water surface slope is considered as S, and basically using what is known as the Bernoulli's equation. This is the equation of fluid mechanics. I will talk about it a little later on, but I just wanted to show this is the equation. The Manning's equation is used to get the discharge and the water level. This is basically a very simple way of getting the water level for the different discharge. Okay, now I just want to go to a little bit development of collecting data, as well as what is the discharge and the stage. So you can actually do it in two methods. This is the indirect method. When you don't have data, you use mathematical fluid mechanics equation. But if you can collect data, you collect data. The red spot are you go to the river. This person is making a flow measurement using a very current meter. The river is not very high, so you can do by what is known as a wading method. But if the river is high, it can be, the depth of the river can be more than your height. In that case, you have to use other methods, using current meter, using cableways. And, okay? So then you measure, all the red spots are, you measure the discharge, then you generate the relationship between the stage and the flow. And this is what is known as the stage discharge relationship. And the stream gauging is process is also given here. And basically what you do is you have a water level here, and for different water level, then you have, so what you do in a river is you measure the water level, okay? Then to convert that water level into flow, you use the stage discharge relationship. Okay? So this is basically the purpose of developing stage discharge relationship. Now, the third, the other hydrological parameter that is important for hydropower project is the sediment. Okay? Because actually floods can destroy your structures, okay? But sediment damage can destroy, you see the turbines, the runners are destroyed, are eroded because of the sediment. This is an example of a hydropower project in Nepal, and Nepal has a lot of sediments. I will have to talk separately with some of you, about the sediment load in the rivers in Mozambique, but I would expect it would not be as high as in Nepal, but still the load, there would be sediment, suspended sediment along in the river. So that is important to measure. What is the concentration? How many milligram of sediment is there in 1 liter of flowing water? Okay, so we have to do that because we need that data to design the settling basins so that we can separate the size of the settling basin, descending basin will depend on the sediment concentration. Because if you do not do that, it will destroy, damage the turbines. When you have these runners of the turbines damaged, the efficiency of power generation is lost, which means for the same discharge, for the same head, you get less power generation, which means you get less revenue. So, and also it will increase the cost of the capital because you have to replace these turbines or you have to repair this turbine. It increases the operation and maintenance of the projects also. Okay. So reduced generation is because of loss of efficiency, also because of you have to shut down. When you have too much of sediment in the river, you may have to shut down the plant. Also because of, you have to do flushing and shut down, and also because in a reservoir project, the live storage is lost. So this is something that would be affected. On the right-hand side, lower figure, what you can see here is the hydraulic efficiency of Chimbrook is really decreased between, the blue one is after a big flood sediment, a flood event, there was a lot of sediment that destroyed these runners and the turbines of the turbines. So the efficiency decreased, so the power generation reduced. So sediment is also a very important design parameter for hydropower projects. Okay. Now, in terms of sediment data, when you have to collect sediment data, you basically collect, there are sediment data is, one is the bed load. Bed load is the sediment, small, larger size sediment that is flows sort of coarse material that moves at the bed surface through sliding, rolling, and saltation, they call it. So it's the bed material. In the river, you have the bed material. It doesn't move, but just above it, slightly, there is with the flow of water, the bed load also moves. Then above that, suspended sediment are relatively fine sediments which are in suspension. And this sediment suspension variation, the concentration varies according to this thing. Just to give you an example, it is important to note that we have to get the distribution of the sediment. What is the size? What percentage of the sediment is more than 0.002, more than 0.02, more than 0.112 millimeter? 2 millimeter and above, I think, is considered sand. Anything above, less than that, is considered silt. So we also have to find out for what flow, what is the concentration of sediment. Sediment concentration, it's basically given in parts per million or milligram per liter. So this data is also an important part of a hydropower project study and design. Okay. Now, this was the hydrology part. Okay. Now, Carlos, is there any question? Do you hear me? I hope you are hearing me. Carlos? No news is good news, they say. Let me just try to call Carlos on.
Yeah, but I was not with my micro close to me.
Okay, thank you. So is there
Yeah.
any question up to on the hydrological part, analysis part? Or I will move to the next slide otherwise.
I think we may take some questions, and also after that we should have a break because it's almost 11 now.
Okay. Okay, whatever. Yeah. So
Hello, Divas?
yeah, okay. That's good for me.
No
Any
question?
Yes, please. Yeah, please. Can you find out if there is any question?
Alguma pergunta, colegas? Antes de irmos para o intervalo? Alguma pergunta, colegas, antes de irmos para o intervalo? There are some questions, Divas.
Yes, please.
I'd like to hear something from you about the possibility of two-stage on the flow duration curve. We talk about possibility of choosing 95% of the duration, and if we could choose two-stage according to two-stage, okay, 95% and something about 6% of the flow duration curve, taking into account the efficiency of the turbines. For example, Kaplan turbines. What's the possibility of choose these two possibilities, these two stages? I don't know if you understand me.
Not clearly, actually. You said something about flow duration curve. Yes.
Okay. Could you go back to the flow duration curve?
Yes. Yeah. Can you see the flow duration curve?
Okay. If we could choose, okay, show another one. Not this one.
Which one?
Okay, go back.
Yeah, this is the flow duration.
Okay. Okay. There's the flow duration. Flow duration curve. Not hydrological flow duration curve.
Yeah. Okay. Yes.
Okay. Okay. You said that uh, for our sizing, for sizing of the our turbine, we need to
Yes.
consider the 95% of the flow. Né? If we could consider two states, for example, 95 and okay, for example, 6%. Okay, it taking into account the efficiency curve of the turbine. What's the possibility of doing this?
Yes. Okay. Yeah, I think I get your question. I think I get your question. Yes. What your question was, suppose we use the design discharge of 95% or let's say 80%. Okay. Right. Right. So now if you design for 80%, 3.5 cubic meter per second, but 20% of the time you have less than 3.5. Okay. So during that time, your efficiency of turbine efficiency decreases because your rated discharge or design discharge is 3.5 cubic meter. So tomorrow, I think I will cover this. So there is a relationship between the rated head, rated discharge, and the actual discharge. The efficiency will decrease. So, but what you can also do is you can have more than one unit. Let's say you have two units, okay? Not one turbine, but two turbines. So one turbine will have half of this, 1.75 design discharge, and second turbine will have 1.75. So when you have 3.5 cubic meter per second of water available, then you generate using two turbines. But when you have, let's say, 1.9 only, then you generate using just one turbine or half of that. So this is an optimization problem. But normally for when you design for 80%, 90%, or 95%, the number of turbines doesn't really make a difference because the flow variation is not much. But if you design, if it's a project connected to the national grid, you could design up to even 40% dependable flow because you want to also generate when there is high flow, and you can, whenever the flow in your river is less than your design discharge, you can use other sources like from the reservoir, from the Kahora Bassa dam. So if you have storage project, run of the river project, a good mix, then you can even design for 40%, 50%. In Nepal, in my country, there are projects nowadays designed for 40% reliability also. So it generates more energy during summer, but less energy. I mean, during wet season, it generates more, but during dry season, it generates less. And also, one thing is, I think this is something very important, we'll discuss later. Even in the case of Mozambique, if it is grid connected, if you design your project for 40, 50% dependable flow, at least in the wet season, then you can reduce the thermal generation. In dry season, there is more thermal generation because you have a good mix of thermal and hydro, I mean, a mix of hydro and thermal. So that is important. So it's in a system planning perspective, individual project optimization, it can vary. So yes, when the discharge is less than the rated discharge, the efficiency changes. And tomorrow I will show you the efficiency curves for different discharge. When the head changes, it changes. Tomorrow I will show you that, and I will discuss a little bit more on this. Yeah, Carlos,
Yes, we
did
could
I
hear you.
answer the gentleman properly, or
I don't know if there are some more questions.
Yeah, please let me know. I mean, I'm here.
Okay, maybe we break now
Okay.
for 15 minutes.
Okay.
At 11:15.
Yeah. So good. I'm here, and let me know when you're ready. But I'll start at 11:15.
Okay, thank you.
Thank you so much. Okay. Thank you.
Sim, não é para por aqui. Então, essa fica ali. Mas ali à frente pode pôr duas, três mesas. Exatamente.
Okay.
Hello, Divas?
Yes, Carlos, I'm ready. You're ready?
Yeah, it seems that we have to put everybody in the same room to avoid that we have problems in the room up and then downstairs and then again upstairs. So we decided to organize that everybody sitting in the same room, about 40 people.
Okay,
So
yeah, because I don't see room 2 connected now.
Yeah, but room 2 is the most problematic one. Usually they don't have a good connection there. When we say down here, they say, tell me, no, we are not yet okay. So let's try to avoid this.
Okay.
By having every ask you please some more minutes, and then you have to take it from the lunchtime. We see.
Sure, sure. Yeah, just let me know when you are ready. I'm ready to start.
Edelson? Edelson? Hello, Edelson? Edelson? Tem lugar aqui? Tem lugar aí? Tem lugar aqui? Podem vir para frente alguns? Tem 3, 4 lugares aqui à frente. Tem lugar aqui à frente. Tem lugar aí? No canto, já. Aqui também tem lugar. Adelson? Desceram todos? Ok.
Já desceram todos.
Já desceram todos? Ok.
Sim.
Tem mais um lugar ali, por favor. Mais outro lá. Está alguém aí fora, Adelson? Aí fora está alguém? Algum colega ainda a chegar? Não é? Os que estavam lá em cima. Divas? Alô, Divas? Alô, Divas?
Yes, yes, sorry, I was muted. Okay, thank you.
Alô?
Hello, you can hear me now?
So, I hope you can see everybody in room 105.
Yes,
I
yes,
will ask
more or
the
less.
partner to disconnect room 2, but you can disconnect room 2.
I think room 2 is already disconnected. Room 2, computer 2,
Okay,
no, it's not disconnected.
yeah. Just disconnect. Not disconnect. But we'll do that. If not, we will try to do it from here. I think we can continue now. Divas?
Yes, okay. I start, okay? Okay, thank you very much. Welcome back from your break. And I hope you can hear me. If you cannot hear me, Carlos, somebody, please let me know as soon as possible. Okay?
Clearly, we can hear you clearly.
Thank you so much. Thank you so much. It feels good. Okay. As we mentioned in the I think the session yesterday or day before. I mean, basically, when you calculate the power and energy, we basically look at the power equation where it is efficiency multiplied by specific weight of water times QH, which gives you the kilowatt hour. Now, efficiency is a product of hydraulic efficiency, turbine efficiency, and generator efficiency. And basically, we have the rated, the gross head. Gross head is the elevation difference between the water level at the intake and the turbine axis for Pelton and the tailwater level for reaction type turbines. So net head is the gross head minus the system head losses. Mind you, the main objective of designing the civil structures, which will be started today and maybe will flow to tomorrow, is basically how do you design the intake, the canal, the forebay, the gates, everything, which will have the minimum system head losses, so that whatever head we try to get maximized up to the turbine. Now, rated head is the head at which the turbine functioning at full gate opening will produce a power output as per the name of the turbine. This is the rated head. So design head is the net head under which turbine reaches peak efficiency. So this is the design head. And basically we decide on, when you do the design head, we decide on your, based on the flow frequency analysis, flow duration curve, we get the design head, design discharge, and the design head is the head at which the turbine reaches its peak efficiency. In the case of ROR, basically design head and weighted head are more or less the same. Overall efficiency we talk about. Okay, this is, we know how you calculate the power. Now energy is power multiplied by time. No? So that it gives kilowatt, and you multiply by hour, it gives you kilowatt hour. Okay, that we know. But the interesting part is, now, as I mentioned earlier, how do you select the design discharge? Okay, from the flow duration curve, we saw that if you want to make it 90% dependable, we will design for 2.5. If you want to make it 60% dependable, the design discharge will be 5.5. If you want to make it 40% dependable, the design discharge is 9.8. So we have this option. Now, actually, what is the optimal capacity? Okay, because if you design for 2.5, the kilowatt, if you design, and let's say this is just an example, practice example, I assume a net head of 20 meter, approximately Majau mini hydro. And I also assumed an overall efficiency of 0.85, right? Multiply by because net head already considered this efficiency 85 is the turbine efficiency and the generator efficiency. Now, if you design for 2.5, the red one, the installed capacity will be less than 500, about 400 something, 80, 85 kilowatt. Now, if you use a 5.5 design discharge, it will be almost 900 something. Okay. Now, if you use 9.8, it will be more than 15, about 1600 something. Okay. So now you can design the same project for less than 500 kilowatt, little less than 1 megawatt, and little more than 1.5 megawatt. Now, how do you select whether you want to make it 400 something, 480, 900 something, or 1600 something kilowatt? Now, this depends on two things. No? One is, of course, the cost. Now, if you design for a smaller capacity, design at 90% dependable, the size of your waterway, your powerhouse, the turbine, everything is less. If you design for 5.5, the size of the waterway, everything, intake, waterway, turbines increase. So the cost increases. And similarly, if you design for 9.8 cubic meter per second, it also increases. But you also generate, and the other thing is, if you design for 90% dependable flow, what you will see is 90% of the time you will generate maximum capacity, the red line, okay? Then some part of the time, 10% of the time, you cannot generate in full capacity, okay? Now, if you design for 5.5, okay, 60% of the time, okay, from 60% of the time. So out of 365 days, 60% of 365 times 0.6 will be 219 days. It generate full capacity, almost 1 megawatt. Okay, but remaining 146 days, it will generate less. Okay, according to this curve. Okay, and similarly, if you design for 9.8, it will generate around 1600 kilowatt for 40% of the time. And so 40% of 1 year is 146 days. It will generate full capacity. The remaining days, 210 days, 19 days, it will generate less. Now the question is, if it is an isolated system, okay, mini grid. So the supply, because if this is the demand throughout the year, you will have deficit. So you have to find other way to meet this. I mean, traditionally, what you do is you probably, if the demand is high and you don't have any other project, you have a thermal system or something that is where in other months you meet by the thermal system or by importing from another system or by using a reservoir project, storage project. So this, what is known as the power duration curve, is depending on the design discharge, your dependable energy, the generation of the energy will vary in this way. So this is an optimization problem. And also you have to be careful. Just because you generate this capacity, it doesn't mean it will be used. The reliability of this capacity is low. It's only 40%. The reliability of this capacity is 60%. The reliability of this capacity is 90%. So these are very important parameters that needs to be considered when you design the installed capacity. What is the optimum installed capacity? For example, the Majao hydropower project is designed for, I think, 4.5 cubic meter per second, which is available 12 months in a year, always. So it generates 585 something kilowatt, always. But you could design Majao for a higher capacity. You could design Majao for maybe more installed capacity, but the reliability or the exceedance probability of that power will be different. Okay? So this is a very important part of a hydropower design capacity optimization problem. Now, if you look at the monthly generation pattern, okay, the blue one is the red here. Sorry, I should have put the same color. I'm sorry. The blue one for is Q40 capacity. So all 12 months, it generates more or less the same, okay, because it's like a little bit. And the orange one generates, because 60, it generates most of these January, February, March, April, it generates full capacity. Whereas Q40, it generates 3 months, 3-4 months, it generates full capacity. There is some fluctuation here. Normally, actually, this should be more or less same, but because of some variation in the month also, so the quality of data is important. So now the question is, this is the energy generation pattern in terms of megawatt hour, okay, it generates here. But now, what will you, suppose your demand is 30 megawatt hour in all the months. So what will you do in 1, 2, 3, 4, 5, 6 months? Half of the month you have 30 megawatt hour, but other 6 months you have less than 30 megawatt hour. So this is what is known as a power mix. So if you have multiple power projects, hydro, different type of hydro, different size of hydro, reservoir hydro, solar, bioenergy, thermal also, then you could have an optimal mix to design. And if you look at EDM's master plan, power sector master plan for the next 20 or 30 years, I see that they have planned, because in the national grid, you can have a mix. But for a rural isolated grid, it may be a different story, okay? So this one, I just wanted to give you an example. So now I just, sorry, what happened to my, okay. So is there any question on the selection or the variation of, okay. Is there any question on the variation of the energy and power generation? Because I'm about to come to an end of this particular part of the energy calculation. Carlos, any question, any comment on this from the participants?
Thank you, Divas. Thank you, Divas. Alguma pergunta, algum comentário antes de ele passar para outra matéria? É só levantar a mão ou ligar logo o micro. Quem não tiver o micro por perto, levanta a mão para receber o micro. No question, at least
Okay.
in the room.
Yeah. Okay. Thank you. No, that's fine. Okay. I just wanted to, it's good. Okay. Okay. Now, this is I'm just going to close. I have one request. I mean, I call it an assignment, but it is just a request that I would request. I mean, it doesn't have to be an individual assignment, but as a group, from what I understand, in the participants, you have participants from EDM, FUNAI, ERM, from different organizations and with different backgrounds, okay? I would request you, I mean, as a, maybe Carlos, you have to talk to the participants, and it could be a group work in about 1 week time, next, not this Friday, next Friday. If you could give me, I mean, collect whatever is available. Like for Majau, we have some data. So if you could collect and compile the operational status and key selling features of mini hydro projects in Mozambique. The reason I do this is, if you can give this, I would like to use these projects as case studies in the exercises later, and new ones, okay? The information that would be useful would be the location, the latitude and longitude, name of the river, what is the catchment area. In case you don't, some information is missing, if you give me the latitude and longitude of the location, of the where location, dam location, then I can use GIS and help, and we can do it. I can show you how we delineate the catchment area. Okay, that will be very nice. Then what is its status? Is it operational, not operation due to, like Majau, there was some problem. So anything, if you could, what is the installed capacity and annual generation? And also if you could generate the pattern, whatever is available. Design, discharge and head. What is the design discharge? What is the turbine type and make? What are the population? How many people served by this? What are the names of the settlements? What are the end users served? What are the other water uses? Any additional information, photograph. If this is not an assignment, I'm sorry, I called it an assignment, a request is, let's do a group work where you can provide me this information, let's say in 1 week time, because I have one class tomorrow on Friday morning, then next Friday on 27, I have another class. So then I will use this information and work with you during the exercise. Carlos, is this possible?
Yeah, I think it's possible, but you may have to put this in a written form
Yes.
for the email groups. Everyone get the same assignment, I would say.
Okay.
And then they can help each other by collecting information and be ready for Friday next week.
Yes, that will be very nice. Thank you. Yeah, thank you very much.
Just ask if someone. Let me just ask if someone wants to comment on that.
Yes,
acho que todos perceberam o pedido para se resolver um exercício prático que está ligado ao álbum de Moçambique. Ele gostaria que, como uma espécie de trabalho de casa, ele vai escrever para todos vocês, para aquele e-mail do grupo, em que ele vai colocar a necessidade de recolha de dados. Quais são os dados que devem ser recolhidos? E ele diz, por exemplo, Majau, mas não tem que ser somente Majau. Quem tiver conhecimento de uma outra estação de produção de energia pode também usar esses dados. O importante é que todos vão fazer o mesmo tipo de exercício e, se for Majau, então todos vão fazer sobre Majau. Mas os dados têm que ser recolhidos em grupos pequenos ou grandes e ser os dados todos partilhados para todos. Na sexta-feira da próxima semana, dia 27, ele então, depois dos colegas serem enviados os dados para ele, ele vai dizer qual é a data que deve enviar, ele então a trazer um exercício específico para o trabalho do grupo na aula que teremos na sexta-feira da próxima semana. Algum comentário? Alguém quer acrescentar alguma coisa? Ou chamar a atenção de alguma coisa? Okay, it seems that they all understood. So they will be waiting for your kind of assignment.
Okay.
With questions and instructions about the deadlines and so on.